Hi, I'm Mrs. Burns, and welcome to Lecture 2 of our Science 10 Chemistry unit. Today we will be looking still at Chapter 4, but diving in a little bit deeper to Bohr diagrams. Now, in our last video, we talked about the periodic table of the elements, and we know that the periodic table shows different patterns of electrons in atoms. So today our big ideas, the things that I want you to walk away having a better understanding of are how are these elements arranged into their different groups, and how do you know which elements are more likely to react together? So here we have this studly guy, Niels Bohr, and he's the one who invented Bohr diagrams. He was a Danish physicist who studied the structure and behavior of atoms. And he discovered that electrons were arranged in what he called shells. And he was so excited about this that he actually postponed his honeymoon so that he could write a very famous paper on it. He later went on to win the Nobel Prize for his work on electron shells. So that's pretty exciting. So the Bohr diagrams, the things that he invented, show how many electrons are in each shell surrounding the nucleus of an atom. So remember, we talked about this last day, that the nucleus is right smack dab in the center of an ion, and the nucleus has protons and neutrons. So let's write this. Nucleus has protons and neutrons. Now, surrounding the nucleus, we have electrons in these shells. So, electrons found in these shells. And the shells form the bulk of the atom. Now, you may notice that this diagram for potassium has 19 protons and 20 neutrons in it. On the left here, this guy, this yellow circle in the middle, that's our nucleus, and then all the gray dots are the electrons surrounding. And again, here is a third way to draw the potassium as a Bohr diagram. We have K, which stands for potassium, 19 protons, 20 neutrons, that would be our nucleus. And then each line here is a different shell. And this tells us in the first shell there are 2 electrons, then 8 in the next, then 8 in the third, and then 1 electron in the last shell. Now we know that in a neutral atom, the number of protons is equal to the number of electrons. So that means that for an example like this, potassium, if it has 19 protons, we're going to draw 19 electrons surrounding it. So let's double check. We have 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Woohoo! So the first shell surrounding the nucleus can hold up to 2 electrons. The only element that holds 1 is hydrogen. So that is our exception. Then the second shell, then the third shell, then the fourth shell, etc. can hold up to 8 electrons each. So the second shell will hold 8. Once we get to the 9th, the next electron will go into the next shell. Once that third shell hits 8, then the next electron will go into the 4th shell. So let's draw neon as an example. If we have 10 protons and 10 neutrons in neon, there is our nucleus. Let's draw our electron shells in green just to make sure we are knowing the difference. We have 1, 2 electrons in our first shell, but we know that we need to draw 10 electrons because that's how many protons we have. So draw 10 electrons because 10 protons. So 1, 2, so we need to make another shell. 3, 4, 5, 6, 7, 8, 9, 10. All right, there we go. We've got 10. So we only filled 2 shells, and both shells are full of their electrons. So table 4.2 on page 174 does remind us that atoms and ions are different. Remember, if we're going to draw an ion, then the number of protons does not equal the number of electrons. This is very important to take note of. So let's draw lithium as an example. If we have a lithium atom, 3 protons, has 4 neutrons, and then a lithium ion. I'll just do this at the same time so I can have the same color. So lithium atom, 3 protons, means that we're going to have 3 electrons to draw. So first shell has 2. Good, we've still got another one. Make another shell. And 3. Wonderful, there we go. But what about a lithium ion? We know that a lithium ion will like to lose 1 electron. So that means that it's going to be left, leaving it, plus 1. So how do we draw this? Well, if it's going to lose 1 electron, we need to get rid of one of them in our drawing. So if we had 3 and we need to get rid of 1, we're only going to draw 2 electrons because one of them got kicked out. So now it is plus 1 because there is 1 more proton than there are electrons, and we will show this with brackets around our Bohr diagram, and then a little plus 1 on the top right corner of our brackets. Now here in figure 4.7 we have a periodic table drawn as Bohr diagrams for many of our elements. The period number, which are the horizontal rows on the side here, the period number tells us how many electron shells are occupied in a neutral atom. So in period 1 we have 1 shell, and here helium, 1 shell. And then period 2 we have 2 shells. So that means that the first shell of 2 electrons is full, so the next electrons have to go to a second shell. In the third row we have 1, 2, 3 shells, and then again in the fourth row you can see 4 different shells. The outermost shell, so the one on the outside, is called the valence shell. We did come across this word last day. The electrons in this shell are called valence electrons. The groups, or the vertical columns, so let me just remind you here, the groups are here at the top going down. These purple circles are our groups, so this would be group 17 here. The groups tell us how many electrons are in the valence shell. Now, when thinking about figure 4.7, we notice that group 1 has 1 valence electron, group 2, 2 valence electrons, 3 valence electrons, group 13, 3 valence electrons, yada, 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 all the way down to group 18, which are the noble gases that have 8 valence electrons. So the noble gases have a full valence shell. They have a full 8 electrons in their outside shell, except for helium, which has 2 electrons in its outside shell, which is still a full valence shell for helium. So electrons will like to complete shells by lining up as pairs, well, except for hydrogen because it only has 1. So why do electrons pair up? I thought electrons are negative. Don't negative and negative repel each other, kind of like a magnet if you put 2 of the same side together? Scientists back in the day were surprised at this as well. They really wondered why were these electrons pairing up. But then upon further research they found that each electron has little differences in its magnetic properties that allow for this. So when 2 atoms move closely together, we call this a compound. 2 atoms together are a compound. So compounds form when 2 atoms move close together. And the valence electrons, the outside electrons, are interacting, and we end up having a bond form, and this would be called a chemical bond. So we talked about atoms the other day wanting to be stable. They're most stable when their energy levels are low. So this happens when they have a full shell of usually 8. Helium is our exception of 2, 8 electrons. So in order to get that get those 8 electrons in that outer shell, metals will give up some of their extra electrons, and we call these cations. Nonmetals will gain those extra couple electrons, and we call these, oopsies, anions. And finally, atoms can also share electrons. So there are 2 main types of compounds. One would be ionic and the other covalent. What are these ionic bonds? Ionic bonding usually occurs between a positive ion, which is usually a metal, and a negative ion, which is usually a nonmetal. One or more electrons are transferred. This is our key word here, that an electron is actually given away to a different atom. And usually it's our metal that is giving its electron away to the nonmetal. We can use Bohr diagrams to show this. So in sodium and chlorine, these 2 different atoms, we see that sodium has 1, 2, 3 shells, and in its outer third shell there's only 1 electron. Whereas in chlorine we have again 1, 2, 3 shells, but in its outer shell there's 1, 2, 3, 4, 5, 6, 7 electrons. So neither of them are at 8, and both want to be at 8 for their outer shell. So do you think it's easier for chlorine to give 7 electrons to sodium, or is it easier for sodium to give 1 electron to chlorine? I hope you said sodium. So sodium will give its 1 outer electron to that little vacant spot for chlorine. And now sodium has 2 full shells, and its outer shell now has 8 electrons. And because it has lost 1 electron, we put the brackets around it and show that it has now 1 extra proton than it has electrons. And now chlorine has become an ion as well, and it has 1 extra electron shown here. So we do draw it as a full outer shell of 8 here, and then we indicate that this ion has 1 extra electron than its regular neutral atom. When an atom gains or loses an electron, we call this an ion, and we need to show the ion charge like I just showed you on the outside of the brackets. So don't forget that, please. Because sodium is losing an electron, do you think that this is the metal or the nonmetal? Remember that metals are cations and the nonmetals are often anions. So which one do you think is the metal? Well, sodium is losing the electrons, so it will be the metal cation, and chlorine will be the nonmetal anion. On to our second type of compound. This is covalent bonding. So instead of giving away an electron, they are shared. So the electrons are shared between a couple of atoms. So typically we see this between 2 nonmetals. The unpaired electrons from the different atoms will come together, and both atoms are now attracted to that pair. We call this the bonding pair. This is the pair that completes that bond between those atoms. Now the lone pair is what we call the electron pairs that are not shared with another atom. So for example, here in water, we have this pair between hydrogen and oxygen. Hydrogen usually only has 1 electron in its outer shell, and oxygen usually only has 6. But if it shares with these hydrogens, Then the oxygen can now have 8 in its outer shell, and the hydrogens can have 2 in its outer shell, which is more stable than just having 1. So these pairs here are called the bonding pair. Bonding pair. And then the extra pairs on the outside here, these are still paired up, but they're just together. These are the lone pairs. So this one here is a lone pair. Well, there you go. You just learned about Bohr diagrams. Please come to class next day ready to practice and to discover this idea a lot further. Next video, stay tuned for Lewis diagrams.